Many laborers are fighting hard against violent ocean currents to complete the construction of an underwater bridge pier. Can you spot a mistake made by the chief construction engineer? This mistake will result in a catastrophe. Welcome to one of civil engineering's most challenging tasks, underwater construction. Even though we call it underwater construction, today's engineers avoid working directly in the water when building an underwater structure. Instead, they remove water from the construction area by building a temporary dam called a cofferdam. Working directly under the water is far from practical, so the next question that arises is how to build the cofferdam under the water. The first step is to erect guide piles with the help of a pile-driving hammer machine. These guide piles provide guidance for the construction of the cofferdam. Then, workers drive sheet piles into the soil using the same machine. These sheet piles have interlocking connections at both ends, which minimize water leakage. The sheet piles are driven into the ocean bed until they reach the bedrock. The piling order is from the corners to the center, maintaining alignment this way. Have you noticed anything special about the pile-driving hammer machine? It isn't just pushing the sheet piles down, it uses vibration to penetrate the soil. The machine's specialty lies in its two counter-rotating eccentric weights, which induce vibration. A flat-surfaced ship called a barge is employed to carry machinery and components required on the construction site. Now, we're ready for the big phase of the construction project, pumping out the water from the cofferdam. However, before doing all this work, the engineers had a major assignment to complete. They had to conduct a detailed geotechnical study of the soil on which the cofferdam would be constructed. They selected land that could carry the load of the permanent structure. The most commonly used test for measuring soil strength is an in situ test called a cone penetration test. The cone penetration test device is placed on the ocean bed, and the conical tip penetrates the soil while sensors send back friction and soil resistance values. The engineers continue the penetration until they reach the bedrock, indicated by a sudden jump in resistance values. This test informs the engineers how deep the sheet piles must be driven. They should reach the bedrock. Returning to the project, the next step is to begin pumping water out of the cofferdam. As the water level lowers, you may notice water leakage between the sheet piles. This is due to the differential pressure of the water. Single-layer sheet piles are failing, so a double-layered cofferdam is required. The space between these sheet pile walls is generally filled with granular material like sand, gravel, or broken rock. This double-layered cofferdam will effectively resist water leakage between the sheets. Now, let's remove all the water from the cofferdam. Unfortunately, the entire cofferdam collapses inward. Earlier, when water was present on both sides, the force acting on the cofferdam due to water pressure was cancelled out. However, once the water is removed, a huge inward force destroys the cofferdam. The inward collapse of sheet piles can be prevented by erecting a bracing frame structure alongside the sheet piles. The bracing frame system comprises components like wales, struts, and braces, with connections bolted together. These horizontal members, called struts, provide lateral support that resists inward movement of the cofferdam walls. Now that the cofferdam is super strong and has reached the bedrock, it's time to remove the water again. But can you predict what will happen next? In a small but cute experiment, when I remove water from the cofferdam, you can see a U-shaped movement of water particles below the cofferdam. This occurs due to water pressure differential. The same thing happens inside the cofferdam as well when water is removed. Water seepage inside the cofferdam is inevitable, and preventing it is challenging. Therefore, we must continuously pump out this seepage water. Once the soil above the hard strata is removed and concreting is done on the hard strata, our underwater project is half done. This is called the concrete seal course technique. The concrete seal course also acts as a strong footing, preventing any water leakage. The removal of soil from the cofferdam is typically done using clamshell buckets, operated by an excavator. Doesn't the operation of the clamshell bucket look pretty cool? The next stage involves constructing the concrete seal course. To ensure the concrete seal course bonds strongly with the bedrock, we need piles that penetrate into the bedrock. The vibrating hammer machine is used again to push hollow steel pipes into the bedrock. The hard rock within these cylinders is removed using an auger machine. Reinforcement bars are then placed into the cavity, and concrete is poured. Once the piles are ready, the concrete seal course is built above them. Since seepage water is present at this base, the seal course concreting is done using the Tremy method. This includes a hopper bucket and a long segmented pipe. Specialized cement with high workability is used for concreting the floor. A thick plug is installed at the bottom of the Tremie pipe to prevent water from entering the pipe. After some time, the pipe is lifted with a jerk, causing concrete to pour down and the bottom plug to be removed. During this process, the discharge end of the Tremie pipe is continuously kept submerged in the concrete to minimize mixing with surrounding seepage water. Now that the concrete seal course is ready, it's time to tackle the remaining construction work. The water seepage is efficiently blocked by this structure. Workers lay out the skeleton of high-quality reinforced bars to construct the footing shaft of the bridge pier. Because the bridge pier structure will remain in the water, engineers ensure that the materials used in construction are of the highest quality to withstand water pressure and the load of the bridge. As the skeleton of the bridge pier progresses, arrangements are made to pour concrete into the structure. Once the concrete is fully poured into the skeleton, the structure is kept undisturbed to gain strength. Typically, a bridge pier takes 14 to 28 days to gain full strength. Once the bridge pier has gained enough strength, the cofferdam is no longer needed and becomes an eyesore, so the engineers remove it. However, removing the cofferdam below the level of the concrete seal course could affect the strength of the entire structure. As a result, engineers cut the sheet piles at this level. Finally, the strong bridge pier is ready to support a heavy bridge. I hope you enjoyed this video on underwater construction technology using cofferdams. However, there are different kinds of underwater construction technologies, such as caissons and pile foundations, which we will cover in a different video. Before leaving this video, please consider supporting us on Patreon, it will make a difference. Thank you, take care, and bye-bye.